In the lecture 6, we'll actually talk about the a concept called deadlock. So first we'll discuss what is a deadlock, then we'll discuss what are the how we can actually identify deadlock and solve it. So basic concept about the deadlock: system model, deadlock characterization, resource allocation graph, and methods for handling deadlock, deadlock prevention, avoidance, detection, and recovery. So this chapter is all about deadlock. Now, first of all, what is a deadlock? So this is actually a new concept for you, that in an operating system a deadlock occurs when a process or thread enters a waiting state because a requested system resource is held by another waiting process, which in turn is waiting for another resource held by another waiting process. So the definition actually might seem a little bit difficult, but the explanation is very simple. Let's assume you have two printers. Okay. So already two processes are using the printers. Okay, or already one process is using the printer. So what happens, another process is waiting for the printer. Okay, so here as you can see we have two tape drives. Okay, process P1 and P2 each hold one tape drives and each needs another one. So each process needs two tape drives. Okay, and each already have one tape drive and needs another one. So what happens, that as he needs another tape drive, he will not actually give up one tape drive it already has. In short, if a process needs two printer to work with, and the he already have one printer, so one printer is already allocated to each process, and they are waiting for another printer to be empty. Okay, so that they can start doing their work. But the problem is the another printer is already allocated to another who is waiting. In that case, both of them are keep waiting forever. So this is the concept of deadlock. Now we will see one more visual representation. So here you see, if I look at the bridge crossing example, okay, so this is the two side of the bridge. Okay, so the car is trying to actually cross one another. Now, as you can see, if one of the car has to pass, okay, either this car, let's name it car number 1, and this car, let's name it car number 2. Okay, either one of them had to actually go back and make space for the car. So let's assume he has to actually go back here, or he has to go back here to make space. But both of them are actually wants the other people to go back. Just a regular scenario in Bangladesh. Okay, so like everyone wants that you go back. You say no, I don't want to go back. You go back. Okay, so both of them are actually waiting for the other car to go back, and as this car one is not actually decided that I will not go back, you have to go back. But car two is also said no, I will not go back. Okay, I will not give up my resources. You give up your resources. So this is like the printer example. He already has one printer and waiting for another printer. Okay, so he already have half of the bridge, crossed half of the bridge, and this one is also same. So the question is that how it can be solved. So this is the scenario of deadlock. So that it's almost like a traffic jam, the stuck in the traffic jam. So basically what you have to do is like either one of the car has to move back so the other can pass, but none of them will move back. Same way as the printer, that uh, one of the printer has to be actually one of them have to actually give up the printer the resources so that other can actually do the work, but none of them will actually give up the printer, and in that case a deadlock happens. So what is the difference between other type of interruption or traps with the deadlock? That in other types of interruption the computer actually knows what to do. It actually either send a process into a termination state or in a pause state or so on. But in case of deadlock, okay, what happens, the computer actually the operating system actually doesn't have any uh, viable way to solve it up. So traffic moves into one direction. Each section of the bridge can be viewed as a resource. So taking one printer, taking another printer. Now several cars may have been backed up by deadlock occurs. So if they have, if it now suddenly, let's think that if he wants to back up, okay, what happens, that this space have to be empty. That means this car has to move back, and if this wants to go back, this two car has to move back, which have many more car in the back. So sometimes it might not be possible as well to move back. You might ask, sir, why not just go into this direction? Okay, this direction is for the ongoing cars. Okay, It's not possible to go to this direction or this direction. So the problem is, if this car wants to, even let's say this is a very, he's a very nice person, and he will, okay, let me move back. But problem is, there already, this space is already taken. Okay, he cannot move back in this space. If he has to move back, this car has to be, this place has to be empty. And if this car wants to move back, this place have to be empty. In this way, this is a huge line. Every car has to move back, which they might not be able to do. So these are the scenarios when a deadlock can happen, that every process needs an resource, okay, but it's unable to give up the resource because it needs another one to finish its task. Unless it's finished, it cannot give up the resources. Now, there's one way we can solve this. We can actually make it a suspended process and release all the resources. But sometimes it's not even possible to do that as well. So this is the basic idea about the deadlock, that the operating system, okay, have different processes that are waiting for resources that has already taken. And as the resources are already taken, they will not be returned. So they will keep waiting, and so on. Now, for here, we will actually use to allocate the resources, we'll use R1, R2 up to Rm. Okay, the resources might be CPU cycle, that may be memory space, maybe IO devices like keyboard, mouse, and so on. So we will use R1, R2 for all types of resources. Then each resources has WI instance. What does this mean? We'll come back to that later. So each process utilizes a resource as request, use, and release. So what does this mean? That every time you need a resource, you will request the resource, that I want this. You will either, you'll be using this resource, and after you are done, you will release the resource. So if you need a printer, first you request the printer, then you will use the printer after the request has been granted, and third step, after you are done, you will release the printer. So here is a graph that we'll be using. Let me show you. So for denoting the process, we'll use a circular. Okay, to denoting the resources, we'll use a rectangle. Okay, and this rectangles means that we have 4 instances of the resources. Like if you have a printer, that means you have 4 printer, or I can say that 4 process can use the printer at the same time. So that is what means instances. Request means arrow from process to resource. Holding means arrow from resource to process. So basically we have this 4 types of graph. So okay, I'm actually moved to different direction, sorry. Here, sorry about that. So basically, let me explain this graph. Okay, so first of all, R means resource, P means process. Okay, that's we all know. Okay, so R1 means resource 1, R3 means resource 3, R2 means resource 2, R4 means resource 4. Okay, 1 dot means only one process can use the resource at a time. 3 dot means 3 process can use the resource at a time. 2 means 2 process can use the resource at a time. So we know all about the resources. Let's go through the process. We have 3 process, P1, P2, P3. Now let's explain one by one. What does this arrow means? This arrow means that this process P1 is waiting for R1, or it is requesting R1, and this arrow means R1 is allocated to P2. This arrow again means P2 is waiting for R3, and this means that R3 is assigned to P3. Same way we can say that R2 is assigned to P1 and P2. Now this is all about the graph. Now, is there any deadlock here? How we can actually identify? So as you can see, let's start from one side. P1 is waiting for R1. Okay, R1 is waiting assigned to P2. That means unless P2 is done, as long as P2 is not done, okay, P2 is not done, this R1 will be assigned to P2. Second, P2 is assigned to R3 and R3 is assigned to P3. Sorry, P2 is requesting R3 and R3 is assigned to P3. So if P2 wants to get R3, what it needs to do, it needs to actually, the P3 needs to be finished. That means, let's assume P3 is a process, that needs to be finished. Okay, so when P3 is finished, it will release R3, and when R3 is free, P2 will get R3 and it will start doing its work. And when P2 will finish doing its work, okay, it will release R1, and then P1 will get R1. Okay, and when it will get R1, what will happen? It can finish its work. So basically, it's like a circle which totally depends on P3. If P3 is not done for some reason, okay, if P3 is not done, the R3 will not be released. And if R3 is not released, P2 cannot actually do its work. Okay, and if P2 cannot do its one, R1 actually will not be released. So that is how a graph or resource allocation graphs look like. So in this graph, we have used process resources to actually explain in a graphical way that how each process depends on the other one. Now, here is some, this is called the resource allocation graph, where the resource allocation graph, we
Sir,
have,
graph. Sir,
yes,
please, sir, again.
sorry, let me just cover this one more time. So the set of vertices, instead of actually writing like this graph, sometimes we'll actually use a set of P means the set of process, P1, P2, P3, P4. Okay, so depending on what you are trying to do, is basically you might have 10 process, 12 process. Okay, so in that case, P1, P2 up to P12, you might have only 2 process, so P1 into P2. You might have 4 resources, so R1, R2, R3. So this is actually called set of vertices, where we will actually have 2 sets, one set for the process, another set for the resources. And then request age means Pi to Ri, that is P1 is requesting resource R, and assignment age means Rj to Pi. So in this way, we'll make sure to actually easily explain which one is allocated and which one is waiting to be allocated. So this is called resource allocation graph. Okay, now before we go back to the graph, let's see this example. What does this circular weight means? You see, if you look closely, this is this scenario. Okay, so all the traffic is actually stuck, and how to solve this traffic? So you can say that, sir, to solve this traffic, we have to actually let's assume I want to actually solve this traffic, and I want to make sure these cars, okay, they want to move in this direction. Okay, they will actually go first. So, but the problem is, if they want to go first, these cars, okay, that is moving to this direction, including this bus, okay, they have to be actually pass. Okay, so if they want to pass, okay, these cars will have to pass as well, that are trying to move to this direction. And if this car want to pass, okay, this place has to be empty. So these cars have to be move in this direction. But the problem is, if this car wants to move in this direction, again, this car is actually blocking it. So in short, if you look closely, okay, these cars trying to move here, they are blocked by this type of car. Okay, if I want to move these cars, they are blocked by this car, okay, in this direction. If I want to move, okay, you guys move ahead, these cars are blocked by this direction. And finally, this direction cars are blocked by this direction. So this is actually called a circular weight. That means, you see, there is no apparent solution. All of them are actually trying to move ahead, but stuck by another process. So this is the basic idea of circular weight. Now let us go back to our resource allocation graph. So the resource allocation graph, what we have these resources R1, R2, R3. So first task is you have to write down the resources. So this is all the resources we have, R1, R2, R3, R4. Okay, what does this dot mean? Dot actually means that these are the amount of instances, like amount of printer you have. 3 means 3 printer. That means 3 process can use the printer at the same time. 1 means 1 dot means 1 printer. That means 1 process can use it at the same time. So this is about the dots. And what does this arrow sign mean? Arrow sign means that this P1 is requesting the resource R1. What does this arrow sign mean? From resource to process, that this resource is pointing to P2. So they are actually assigned to P2. So first we have to understand the meaning of each arrows and each abbreviation R1, P1. So I hope we are clear about those. Now, The question is there any deadlock here? How we can understand that whether there is any deadlock here? So at first you will have some trouble, okay, identifying whether you have a deadlock or not. Okay, so how can you do it, whether it's have a deadlock or not? Okay, so basically let's think that first let's start with process P1. So we'll see that what is the condition to P1 to be finished. So we see that to P1 to be finished, okay, we need R1. Okay, so that means it's depending on another process. So let's go for another one. We are looking for one independent process that can actually finish its work on its own. So P1 is not independent, it's waiting for R1, which is being held by P2. So basically we can say that P1 is depending on P2. If P2 is done, it will actually release R1. So let's assume R1 is a printer. So if P2 is done, it will actually release the printer, and when the printer is released, P1 can actually do its work. Okay, same goes for P2. If you see, P2 is not independent as well. P2 is waiting for R3. And what will happen in case of R3? Unless P3 is finished, R3 will not be released. Okay, because R3, the printer R3 is actually assigned to P3. So P2 is also not an independent process. Let's go for P3. We can say that P3 is actually only dependent on itself. Okay, P3 is not waiting for any other processes, and it needs only one process, that is R3, which is already assigned to P3. So now what happens is that the P3 first finishes its work, as P3 is independent process, so it doesn't matter how much time it takes, okay, it will finish its work at some point. And when P3 is done, what will happen? This resource will be free, and when the resource will be free, P2 will get the resource, and when P2 will get the resource, it can finish its work, okay, and it can release R1. And when R1 is released, okay, P1 can actually do its work. So there is no deadlock here, or there is no chance of deadlock, because each process is, one of the processes actually free. There is no circular wait. Okay, so if I go back to this picture, so if there is no problem in if any of the car can move into one direction, there is no problem here. Okay, now any questions for this?